Okay, so let's talk about the absorption of light. Based on the Rutherford-Balmer equation, what we now interpret as the interaction of the electron to the nucleus is that of an orbiting electron that can basically orbit the nucleus via different levels. And the idea is that the electron can absorb energy, and with the absorption of energy, the electron can actually transition from the orbiting, which is closest to the nucleus, to higher orbiting places, energy values, if you will. So the way this works out is that each one of the orbits is assigned a number. And this number, you might have guessed it, this is the principal quantum number associated with the interaction of the electron to the nucleus. So the higher the principal quantum number is, the farther and farther and farther away the electron is located from the nucleus. And what this means is that you need to input more and more energy if you want the electron to go from the first energy level to the second one, or to the third one, or to the fourth one, etc., etc. Now, with the Balmer equation, we can actually calculate what these energies would be. And because of the quantized aspect of the equation, we will only have discrete values that will correspond to these transitions. The in-between is basically not attainable. It's either you have the right value to make the transition or you don't. So, in the case where we go from the first energy level to the second energy level, meaning that n equals 1 and n equals 2 for n initial and n final, we will basically input those values. N final is 2, n initial is 1. What we have to do is to square the values first, so we'll have 1 over 4 minus 1 over 1. And here what I would recommend is that you input the fractions in your calculator and carry out the actual calculation what this is. I'm going to actually stick with the fractions for the discussion just because I don't have a lot of room here to expand with the numbers, but for actual calculations I recommend that you use your calculator. So 1 over 4 minus 1 over 1 is the same thing as 1 over 4 minus 4 over 4, or in other words 3 over 4. Negative 3 over 4. Now that negative gets multiplied by the negative outside of the equation, so notice that the whole thing has turned positive. And what now we have is VC squared multiplied by 3/4. Now if we look at the transition from the first energy level to the third energy level, M final is now 3, and initial we're still keeping as 1 for the time being. So we have 1 over 3 squared minus 1 over 1 squared, or in other words, 1 over 9 minus 9 over 9. And here we'll end up with negative 8 over 9, which cancels out with a negative outside. So we end up with positive VC squared times 8 over 9. If you carry the same premise for N1 going to N4, or N1 going to N5, or N1 going to N6, you're going to find out that in the denominator you'll have the value of N final squared, and the numerator will be 1 less than that value. So 25 on the bottom, 24 on top. 16 on the bottom, 15 on top. 36 on the bottom, 35 on top. And once again, I recommend that you perform the calculation with your calculator and not deal with fractions. But just to save me space, that's what I'm kind of playing with. Now the idea is that each one of these values is increasing in amount. And I'm going to show you in a little bit what the actual numbers are. But the farther out you go, the more energy it will require for the electron to jump to the higher energy levels. This is what the Balmer equation is telling us. The other thing about it is that the value of the energy is positive, and that means that the electron is accepting energy in order to jump to higher energy values. That's kind of important. So absorption of light leads to an increase in the energy. You will be increasing the energy of this atom. Okay? Okay, let's take a look at the hydrogen atom specifically. Okay, the hydrogen atom is the first element in the periodic table, and the atomic number of hydrogen is 1. So this is actually the most simplistic version of all the elements we could be dealing with, because Z, which is the atomic number of the element, gets squared. But if we're looking at hydrogen, Z is equal to 1. 1 squared is simply 1. So basically, for hydrogen, the term of Z squared just cancels out, or kind of goes away because it's just 1. And we can actually bring the value of B inside. And now we have 3/4 times B, 8/9 times B, 15/16 times B, and so on and so forth. Actually multiplying all these values and keeping track of the fact that B itself is 2.18 times 10 to the negative 18 can provide us with some actual energy values. Now, one additional factor that I want to mention before I actually show you the values altogether is something known as the ionization of the element. Now, this element that contains only one electron, you can determine how much energy it would take not to raise the electron to a higher energy value, but to remove it from the atom altogether. And you could still use the Balmer equation for this. The only caveat is that we're going to exaggerate the picture. We say that, okay, the electron, if you're going to remove it from the atom, you're not in energy level 6 or 7 or 10 or 100. By all intents and purposes, if the electron is out of the atom, think of it as being gone. It took off. It went to infinity and beyond. And quite literally, make M final be infinity. Now, infinity squared is the same thing as infinity. Notice that I'm starting with an initial being 1. This is going to be pretty much what you're going to be doing every single time I ask you to find the ionization energy of any one electron atom. So, and final is infinity, and initial is 1. 1 over infinity, for those of you who have taken calculus or pre-calc, you would know that 1 over infinity is the same thing as 0. And 1 over 1 is just 1. So what you end up here with is simply negative B times negative 1, or in other words, simply B. So what it says is that the ionization of hydrogen is equal ultimately to the Balmer constant, which is equal to 2.18 times 10 to the negative 18 joules. Alright, now I'm going to stop the video at this point. In the next one, I will show you a few extra versions of the ionization energy of hydrogen. And we're going to use those versions as new conversion factors to depict energy. Okay, so see you in the next video.